Today's topic is about correlation and regression. So far, we have been talking about independent variables that are categorical or on a nominal scale of measurement. Today, we will begin talking about a family of tests that let us use continuous independent variables. These tests use correlation and regression. As such, we are going to be moving into the world of bivariate statistics, where we focus on the relationships between variables. Instead of focusing on the variance in one variable at a time, we will be focusing on the covariance between two variables at a time. First, we will talk about the foundation of these statistics, the correlation. Correlations can be represented by scatter plots, where each individual is represented by one dot that conveys two pieces of information simultaneously. Specifically, each dot represents a person's value on the x variable as well as their value on the y variable. Scatter plots convey a lot of information about the relationship between two variables. First, they tell us about the strength of an association. When the dots representing each score are close to a line of best fit, there is a strong association. The scatter plot also tells us if the relationship between variables is positive, starting in the lower left corner and moving toward the upper right corner, as this one does. Or it can tell us if the relationship is negative, in which case the dots would start in the top left corner and move toward the lower right corner. A scatter plot can also show us if there are any outliers in our data. In univariate statistics, outliers are scores that are of very low frequency. With bivariate statistics, outliers are scores that are far away from this line of best fit. In this plot, there are not any outliers. I'll add a couple to the plot to illustrate that it does not have to have a very rare score on one variable, but just having a score on y that is unusual given its x. So a score of 2.5 is actually pretty common, but it's unusual for someone to have an x score of 2.5 and a y score of 11. Scatterplots also tell us if the x and y variables are linearly related. That is, if a straight line is the best way to represent their relationship. I've forced this scatter plot to give us a straight line for this line of best fit. Here's what happens if I allow it to have a bend. Although the straight line does a pretty good job, a bend in the line could also work. The bendier your line needs to be to represent your relationship, the less well traditional correlation and regression statistics will work for you. In addition to visually representing the relationship between x and y, we can mathematically represent the degree of linear relationship between x and y using the Pearson correlation coefficient. Our previous univariate statistics were driven by the variance formula. Now they will be driven by the covariance formula. The covariance uses each score's deviation from x and multiplies it by its deviation from y, then adds all of those up and divides by n minus 1. This formula can be tricky, so pay attention to how I would set up calculating it using the table system. First, find each deviation score, and then the product of them. The sum of the product of the deviation scores is the numerator of the covariance formula. After you know the covariance, calculating the Pearson R is pretty easy. It's simply the covariance over S sub x times S sub y. Remember, S sub x is going to be the standard deviation of the x scores, and S sub y is the standard deviation of the y scores. Reflect back on the formulas from earlier modules for calculating these values. Pearson R values range between plus and minus 1. They can be either positive or negative. It's easy to get caught up in the math lingo and lose sight of the basic thing you already know about correlations, that the presence of a relationship does not mean causation. I'll revisit this a little bit as we learn even more new lingo, but for now, just remember, correlation, not causation. Remember, this is because correlation can exist because x causes y, because y causes x, or because something else causes them both. You can calculate a Pearson R for any two variables, but that R might be wrong if one or more of the following factors are present. The Pearson R assumes that x and y are linearly related. To the extent that variables are not linear related, but rather one of those bendy relationships would best represent them, then the Pearson R is going to misrepresent the magnitude of their relationship. When outliers are present, the R value might be deflated or smaller than it should be. The true relationship would be stronger, but the outliers introduce statistical noise or error and make the R value smaller. When you only measure some of the theoretical distribution of either your X or your Y variable, you have what's called restriction of range, and this can also alter your R value. For example, if I measure the correlation between high school GPA and college GPA, but I use only current UGA students, I have a restricted range on my X value. UGA doesn't admit students who have low high school GPAs. So using UGA students only provides a small subset of the whole possible range of high school GPA scores. The fourth factor that can affect the size of the Pearson R is how well you measure your X and Y variables. Think about the things you learned in research methods here. Better scales reduce measurement error, and they allow you to more accurately estimate the Pearson R. Now, Pearson R values often get confused with probabilities because their absolute values range from 0 to 1. But remember that a Pearson R value is not a probability. That means it can't get converted to a percentage. But there is something that can. It's really close to the Pearson R. It's called the coefficient of determination. This value is actually just R squared. R squared can be converted to a percentage that has a really cool, precise meaning, the percentage of variance in X that is shared with Y. This idea of shared variance can be demonstrated with this graphic. When I talk about variance in X, I mean all the reasons that X scores are different from each other. And variance in Y is all the differences between the Y scores. The regions where these overlap is the percentage of variance that is shared between X and Y. We can also use correlations to connect X and Y in a predictive way. That is, we can predict Y from X. This is called regression. You'll be familiar with regression from previous math classes, but we're going to take this concept deeper and apply it to understanding psychological phenomena. The basis of prediction is correlation, so it's using what we know about the correlation between two variables to make estimates of scores. If I know someone's X score, and I know the correlation between X and Y, I can make a better guess about what their Y score should be. Although we use the word prediction here, remember that regression doesn't mean causation. I can statistically estimate your Y score from your X score, but that doesn't actually mean that your X score is causing your Y score. So the regression line shows these predictions that we're making. You can simply go to a value on the x-axis, and then where the regression line, or the line of best fit is, that's the predicted score. So a given predicted Y value is going to have the symbol Y hat. Of course, in your actual data sets, you're going to know the Y values of your X scores. You're not using regression to predict the Y scores of your known data. We're using our sample to create a regression line so that we can predict the scores of other participants or of the population. When a correlation is perfect, every actual Y score falls on this line of best fit. That is, every Y score equals Y hat. However, there are almost no perfect correlations, which means there's usually error or statistical noise. In regression, we model that error as Y minus Y hat. Each score has its own individual error. And we can sum those individual errors to calculate the error sum of squares. Just like with other deviation scores, if we don't first square the prediction error, the sum would always equal 0. So we're going to square this individual prediction error scores, and then we can estimate our sample-wide error. Regression works following the least squares criterion, which just means that that line of best fit gets placed in such a way that the error sum of squares is as small as possible. That line is as close to all of the data as it possibly can be. With regression, we're going to occasionally use some new language. When we talk about predicting Y from X, we might also use the phrase regressing Y on X. Either way, Y is the outcome and X is the predictor. So we can actually calculate the regression line so that if we know X, we can predict Y. In order to do this, with our data, we'll need to identify the slope and then the intercept. Conceptually, the slope represents the change in y for every 1 unit change in x. The formula for b is r times the standard deviation of y over the standard deviation of x. The intercept is the predicted y value when x equals 0. The formula for a is the mean of y minus b times the mean of x. The formulas for the slope and the intercept use the descriptive statistics of your variables to put your regression line in their context or scaling. Now, usually r and b will not have the same value. R values are going to range from 0 to 1 or -1 to +1, but b values can take on any value from -infinity to +infinity. There's only one case when the r and b values will be the same, when the standard deviation of y and the standard deviation of x are the same. Check over your formula to see why this is the only case when r and b can be the same value. Even though they will likely have different values, r and b will always have the same sign. So positive correlations will have positive slopes, and negative correlations will have negative slopes. I talked about the prediction error as the sum of squares. We can also represent it as 1 minus r squared. If r squared is the variance in y that is predicted by x, then 1 minus r squared is the variance in y that is not predicted by x. It's the noise, in the sense that the factors unknown or unmeasured by the researcher are what's explaining that variance in y. As r gets larger, the error gets smaller. When r is equal to 1, the error is equal to 0. On the other hand, when r is equal to 0, there's as much variability in the prediction errors as in the y values. Look back over the formulas for the regression line. When r is equal to 0, what would you guess is a person's y-score? Using these formulas, you can see that when r is 0, b is also 0. And when b is 0, then the regression line boils down to the mean of y. In other words, if x and y are not correlated, then knowing someone's x scores does nothing to help me know their y score. Instead, my best guess is just the mean of y. With regression, we're making several assumptions about our data. First, we assume that the relationship between x and y is mostly linear. If that relationship is not linear, then the Pearson R value and the regression line don't represent it well. The second assumption is homoscedasticity. Isn't that an amazing word? Homoscedasticity means that the prediction errors are not correlated with x. In other words, no matter where you are along the x-axis, the regression line does a similarly good job of predicting y. This graph shows homoscedasticity. See how you move from left to right and the actual scores are pretty similarly spread out around the regression line no matter where you are on x? Here you can see evidence of heteroscedasticity. As x values get larger, the scores are further away from the regression line. There's a correlation between x and the prediction errors. Our final and third assumption is that the prediction errors should be normally distributed. If you made a frequency distribution of y minus y hat, that distribution should have a normal shape, with most of the scores around 0 and a few scores being kind of low and a few scores being kind of high, but balancing each other out.